Alright, maybe we will get started. Let other people join. Okay. Which problem did you say? Seventh assignment, is it?
Yes, yes, in the seventh assignment. Just a second. Just scrolling. Okay. I think 15th question. 15th. This we have to calculate the C star.
Okay.
Uh, According to the calculations given, like according to the formula,
Mm-hmm.
the answer should be nearly 803 something. 803 point. No, no, sorry, 863.1.
Okay.
The answer range is the answer in the solution is 1494.5. Like
Okay.
all the other parameters like the capital gamma, the gamma, everything is matching with their values.
Mm-hmm.
But then the C star, when I calculate, I get 863.1.
Okay. Did they upload the solutions also?
Yes, yes, they have given the solution.
So did you check the solutions?
Yeah, yeah, I checked the solution.
Uh-huh.
Uh, they gave all the values which are used in the C star formula,
Mm-hmm.
like the capital gamma and everything is like the mass and all. It was matching. The temperature was also matching, but then the final C star value,
It's not matching.
they it's not matching.
Okay.
I'm I'm getting it around 863. They got nearly 1494.
Okay. So let's see. Let's just quickly calculate based on here. So this capital gamma is also 0.676.
Yes, yes, yes.
Okay, then it should be straightforward. No, they might have done some mistake. So R naught is 8314.5 divided by molecular weight. How much you are getting? 10.67, is it? Molecular weight. Mm, Molecular weight should be 10.67, I guess. And temperature would be mm, 1308.3 Kelvin. Square root of answer divided by 0.676. So I'm also getting something like
Oh,
1494.
oh, no, no, no. I got my mistake. I got my mistake.
Okay, 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 okay.
I didn't consider the molecular weight. I accidentally considered the whole weight of all the products.
Oh, okay, 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 okay.
Sorry, sorry.
Okay,
It was my
that's
bad.
all right. All right, no problem. All right, we have. I think Ram sir. I think from you there is a echo. Okay, thank you. So, so before we start, does anyone have any quick questions? Does anyone want to ask any quick questions? If not, anyway, we will have time at the end of the class to discuss more.
I have a question. I will, call for that at the end of the class.
Okay, sir, sure. All right. So I think more people will join soon. Let me check my recording. So what I have today is I have two questions here, and both of them are fairly easy. I I took this question so that it will be helpful for you to solve week 9 assignments and also week 10. So uh, the first question is about the injector design. So let's say if you want to go and design an injector for a liquid propellant rocket engine, uh, how would the how would you design the injector? Basically, is what we are going to Even though I say injector design, we are going to just find the total number of orifices we require. Other things are already given. So the first question has consider a shower head injector and determine the total number of orifices required for fuel and oxidizer and mixture ratio of the propellant. So you need to find total number of orifices for fuel and oxidizer, and also we need to find the mixture ratio of this whole propellant. So for oxidizer we have certain quantities given, and for fuel supply we have certain quantities given. We have mass flow rates of oxidizer and fuel, coefficient of discharge and all is given, diameter, pressure drop, all these things are given. So using this we just need to find out the number of orifices, which I think it's fairly straightforward. So um, before we get into solution, let me quickly draw a schematic so that you will better understand the question. So you have something like a shower head injector, okay, which is same like as shower in our household. So basically if I want to draw that, so you will have something like this, and you will have lot of holes through which the propellant flows. Okay, and in this the one injector would look something like this. Okay, so I'm just exaggerating here. So maybe we no need to draw this. So this is the injector, and this is the chamber, combustion chamber, where combustion is going to happen, and flow is going through this. Okay, this is the one injector I'm talking about. Now similarly there are a lot of injectors here and here. Now we need to find out what is the number of this injector, n orifices, for both fuel and oxidizer. Okay, is the question clear? So if the question is clear, then how do we go ahead and solve?
Hello, sir.
Yes.
Yes, sir. Sir, actually, I have a question regarding assignment 8 solution. Should I ask right now or at the end of the class?
So we will complete these two questions. It's a quick. We can complete this quickly, and then after that, at the end of the class, you can ask the question about.
Okay, sir.
Okay.
Thank you.
All right. So for oxidizer, you have mass flow rate of the oxidizer. Let's call it OX. It is 1.44 kgs per second, and the mass flow rate of fuel, which is 0.48 kg per second. Now we need to find what is the number of orifices we require for oxidizer, what is the number of fuel required for oxidizer. Number of orifices required for fuel. How do we find it? Any idea with the given data?
We can
Yes, Pranav, go ahead. We can.
we had we are having the total mass flow rate,
Mm-hmm.
so we can get an average of total average area.
Okay.
Then from that we can calculate. Now we are having diameter of orifice,
Mm-hmm.
so we can divide it by the area of one orifice. So we make it number of
Mm.
orifices.
Okay. How would you? So you want to divide it by the. Uh, but how do you find the area? Total area. We have the diameter of one orifice. We can find the area of one orifice, or cross-sectional area of one orifice. But just mass flow rate dividing by cross-sectional area of one orifice will not give you the number of orifices, right?
Yeah. So we are having pressure. Okay, okay. If mass flow rate is equal to density into volume flow rate,
Mm-hmm.
can we can say volume is equal to volume flow rate can be written as area multiplied by the velocity.
Okay.
Uh, velocity we can use Bernoulli's equation. We have pressure drop.
Okay.
We have pressure drop. We have density.
Okay.
Considering initial pressure as zero, sorry, initial velocity is zero,
Mm-hmm.
can calculate the velocity.
Okay.
We have mass flow rate, we have density, then we can calculate average total area.
Mm-hmm.
We have velocity, we can get a total average area then divided by the area of one orifice.
Uh, Total
Uh, uh,
average. Okay, that could be a way. But the most easiest way is you have one orifice. You can find what is the mass flow rate through that orifice, and that, and then you have the total mass flow rate. Divide by this mass flow rate, you will get the total number of orifices, right? So,
okay, nice.
right. So it's a, so you can easily think in terms of mass flow rate. This is the total mass flow rate entering m dot of oxidizer, and this is the mass flow rate going out. Let's say m dot dash or m dot 1, right? And you have similar orifices everywhere. So basically you can write this as m dot oxidizer, which is total, is equal to uh, number of orifices times m dot dash of oxidizer, right? So now you need to find m dot of oxidizer. For this we can follow whatever you said, which is nothing but rho into q dot, which is nothing but rho a v, and for v we will find use the Bernoulli equation, right? So in that way we can solve this problem. So you are almost there. Only thing is you can use the mass flow rate balance to get this solution. In terms of area, see, that is also one more thing. So the Bernoulli equation, where will you apply? That's also is there, right? So if you apply from, you need to apply across the orifice. You cannot apply from here to here. Technically you can apply, it's going to be same only, but you have to apply it across the orifice. You will get the velocity, you get the mass flow rate through one orifice, and then multiply with the number of orifice, you will get the total mass flow rate. Okay, so that is a easiest way of doing it. So let's see. So mass flow rate through one orifice of oxidizer is going to be rho of oxidizer, area of the oxidizer orifice, and velocity of the uh, oxidizer in the orifice. Now what Pranav said was we can use something called Bernoulli equation. So now another question to you guys, can we use Bernoulli equation here? So so he so is my question clear? Let's say this is 1 and this is 2. Okay, can we use Bernoulli equation here? I know in lectures professor must have used it and you must have derived it, but you should understand why we are using Bernoulli equation. Is it applicable here? These things you should understand, right? So uh, can we use Bernoulli equation? So what are the assumptions we should in order to use Bernoulli equation, what are the assumptions we need to take care?
The flow must be steady.
Okay, flow must be steady, and
The,
And any other assumptions?
It should be for incompressible flow.
Exactly, it must be incompressible flow. Okay, and any other?
Um, no, no friction.
Right, no friction. So basically, it should be it is applicable only in the inviscid flows. Inviscid flows. And any other? There is one more important assumption. It can be applied only along a streamline. Okay, it can be applied along a streamline, and if it is an irrotational flow, you can apply across any 2 points. That is also there. So if it is an irrotational flow, then friction will not come into picture at all. So you can apply along any 2 points. Now, is the assumptions clear? Now we need to validate whether Bernoulli can be used here or not, right? So the flow here, we can assume it to be steady in the orifice, and also the flow oxidizer and fuel are in liquid form when it enters the orifice, so it is incompressible, we can take that. And we are going, so now the question is there a friction or inviscid, is it an inviscid flow in orifice? What do you guys think? In orifice it is an inviscid flow?
Practically speaking, it there has to be some friction.
Exactly. So we have walls here, right? So because of the walls, the friction will be there, and there will be boundary layer developing in this inside the orifice, right? And there might be flow separations happening, and all these things can happen. So ideally, it is not a inviscid flow. So ideally, you should not apply Bernoulli equation at this stage. Along a streamline can be applied, so we can take a center line will be a streamline, so still you can apply this thing, but it is not a frictionless flow. The orifice has friction, right? So Bernoulli equation is actually not applicable in this place, but we don't want to go into a lot of troubles. We don't want to you know uh, find what will be the real velocity profile, what will be the real, so we are interested in just mass flow rate through the orifice, right? So uh, we just want a velocity which is a representative velocity or an average velocity through which the fuel exits, right? So in fact, if you look at here, the velocity profile will be something like, it will be 0 near the wall, and it will be some profile, right? It will be something like this velocity profile. It doesn't have one velocity. Velocity is a function of y. Let's say if you take this as your y, across y the velocity is going to vary, but here we are just going to substitute one velocity. We are just interested in average velocity, so this is nothing but an average velocity. Okay, so just we need to get a representative velocity to find what is the flow rate, what is the mass flow rate in the orifice. That's why we use the Bernoulli equation, and you should be little cautious. The Bernoulli equation, whatever it gives, may not be exactly right. Okay, so let's try to solve this. So I hope everyone is on the same page till now. If you have any doubts, you can stop me anytime. So even though we know that the Bernoulli is not applicable, let's go ahead and try to apply from 1 to 2. Okay, 1 to 2. So when we do that, it will be P1 by rho g V1 square by 2g plus Z1 is equal to P2 by rho g V2 square by 2g plus Z2. Now we will ignore the z1 and z2 term because we are not really interested in the datum, and the v1 here, the velocity 1 here, we are taking it to be what we are taking it to be.
Zero.
It is nearly zero.
Nearly zero, right? Or you can also say it's not exactly zero. We will not put 1 here. In fact, there will be a chamber here where fluid will be rest, right? We take that as our point 1. We do not take entrance of the orifice as point 1, because if the entrance velocity is 0, there won't be any exit velocity, right? So please note that. So that's why we take this to be a tank pressure. Okay, this 1 is nothing but a tank. Let me clarify that here, near the tank, and this is near the exit of the orifice. And then that is how we will ignore the velocity. So we will have p1 by rho g, or p tank by rho g, is equal to p2. P2 is nothing but the, what would be p2? P2 will probably at the exit of the orifice, which will be chamber pressure, right? This will be rho g plus v2 square by 2g, where v2 is what we need to find out. So you can remove that, and then v2 is equal to pt minus pc by rho into square root, where pt minus pc, or p1 minus p2 is the delta p, right? So you can write this as the delta p across the orifice by density. v2 is equal to square root of grad p by rho. This is the velocity Bernoulli equation gives, but doesn't mean that this is the velocity we actually see at the exit of the orifice, right? Because there are a lot of things happen, because there is it's a friction flow, and there will be flows. It will, as I said, it will develop boundary layer. It can break. It can become separate. All these things can happen inside the nozzle, sorry, orifice, and hence your actual flow area would be constricted, and because of that, the overall flow rate will be reduced by a certain amount, and that amount is actually captured by the CD. Okay. This coefficient of discharge, that's why we add a coefficient of discharge in the equation. It's because Bernoulli equation we have applied and got velocity, but that is not the real case. The real scenario is different. So how different is the real scenario based on the our ideal case of Bernoulli equation is what this coefficient of discharge will take care. Okay, so upon substituting all this, and that is how you get mass flow rate of the orifice will be CD times rho A square root of delta P by rho. Okay, this is how you get this mass flow rate. Now you might ask, how do I get the CD, right? So because we just directly, so it's like an efficiency parameter, we just directly put it. So this has to be obtained from experiments. So one has to rely on experiments to find the coefficient of discharge for this kind of orifices. It's going to depend on the orifice geometry, surface roughness, the profile, whether it's a laminar or turbulent, all those things it's going to depend, and that is how we easily get a so all these complex phenomena or all these non-idealities is taken care by the coefficient of discharge, and that is how we easily get this kind of mass flow rate equation which we will be using. Okay, so is that clear?
I think there has to be some two somewhere.
Okay, yeah, I ignored the 2 here. Yeah,
Two in delta P.
so where do I put here? I can put
Two
it here,
delta
right?
P. Yeah.
All right, thanks for noticing it. Yeah, it's good to remember sometimes formula. I don't have the habit of remembering formula. Anyway, so yeah, so this is will be your mass flow rate. So then now you can. That's why coefficient of discharge, delta P, rho, everything is given already. So we can directly substitute it and get the oxidizer. And also similarly, you can get the mass flow rate of the fuel in the orifice. So let's see what is the CD of oxidizer. Sorry, CD of oxidizer orifice is 0.75. So 0.75. Density is 1200, 0.25 megapascal. 1200 5 by 4 into diameter. I think it's 1 mm. Square root of 0.25 megapascal and 1200. 0.25 into 10 power 6 divided by 1200. Right? Did I substitute everything right? Yeah, pressure drop across is this much and this much. Alright. So similarly we can do for fuel. So let me know what is the mass flow rate you are getting for the oxidizer orifice. I will quickly write the fuel also. It's 0.7 1000 0.85 mm 0.15 megapascals. And one more thing is, without the delta P you will not get the flow. So you need a pressure gradient in order to withstand all those viscous forces acting near the wall. Okay, so that's why our mass flow rate has the delta P term in in the formula. So once you find the mass flow rate, you can find the oxidizer, which is going to be total mass flow rate divided by m dash of Ox. Similarly, fuel you can find it as m dot of fuel, m dot dash of fuel. So does anyone have any answer for this?
For oxidizer, I'm getting point 0.14428.
0.14428 kg per second. And fuel?
Just a moment.
I think this is coming out to be 100. So actually you will get 99.8, but you cannot build 0.8 orifices, so you should have 100 orifice.
For fuel, I'm getting some point 00688.
688. All right. So then how much will this come out to be? 0.48 so it should be around 70, I guess. 69.76 you will get, so it's around 70. And then you can find the mixture ratio also. Mixture ratio is simply mass flow rate of oxidizer by fuel, which is already given, I guess. So it's a 1.44 divided by 0.48. So it's coming out to be 3. So it's a straightforward calculation, so I itself did all the calculations anyway. So I hope you guys understand the gist. The gist is, how did we get the mass flow rate equation for the orifice, and we should understand that we used Bernoulli equation, and Bernoulli equation is not right. That's why we multiply by coefficient of direct discharge. Okay, that is the main thing, main takeaway from this problem. Is there any questions you guys want to ask regarding this problem?
No, it's clear.
Okay, thank you. So if there are no problems, then we can go ahead and solve the second question. It is also almost related to injector only. So what do we have in the second question is a liquid propellant rocket which is developing a thrust of 500 Newton, uses MMH and N2O4 as its propellant. Okay, MMH is the fuel and N2O4 is the oxidizer, and the mixture ratio is also given. So the chamber pressure they are fixing, this is the chamber pressure they are going to have. The value of characteristic velocity for this chamber pressure and the mixture ratio is given, 1800 meters per second. The thrust coefficient of the rocket is also given, which means the nozzle is also fixed, 1.5. Determine the throat area of the nozzle, the mass flow rate of MMH and N2O4, and after finding all this, we were asked to find the diameter of the injector holes in the to be provided in the injector for MMH and N2O4. Okay, and the injector is going to be 10 doublet injector elements, which means you will have a fuel and oxidizer injector which is going to which will be in a slanting direction, which is going to create a sheet of what do you call so the two streams of injector and two streams of fuel and oxidizer is going to uh, uh, it's going to interact with each other, and it's going to create a sheet of propellant mixture or the liquid propellant mixture that will further break out and become small droplets. Okay, that is the reason we have this kind of injectors, and droplets can be burnt easily. That's the reason we need to make droplets. The injection pressure of MMH is also given. The discharge coefficient, again, or for orifice the discharge coefficient is given. Densities are given. We were asked to find the what is the diameter. In the previous question we were asked to find the number of orifices. Here we were asked to find diameter. But before that we need to know the mass flow rates, which we are going to use these parameters to get the mass flow rates. I guess this should be straightforward for you guys to solve. So let me write down the given data. Okay, so I hope everyone understood the question. So we have thrust, let me change the thrust to be thrust is given 500 newtons, and the chamber pressure is going to be 0.7 megapascal, and mixture ratio is also given, which is 1.65. Now the characteristic velocity of the propellant C star is going to be 1800 meters per second, and the thrust coefficient is 1.5. Okay, just give me a minute. Okay, I think there is a problem. Actually, I cannot solve this problem. This problem is already in the week 10 assignment. I didn't notice this. I was having a gut feeling that I saw this question somewhere. Okay. Okay. All right. Anyway, I'm not going to solve this problem. Uh, but anyway, we discussed like most of the things. I'm sorry, I didn't realize that this problem is already.
No, but this doubt appearing, I was
Okay.
trying to find out AT is using the relationship CF, EC, and AT. F is equal to CF, EC, and AT. The value of AT comes out to be very, very high.
I see. Okay. Okay. For the same problem?
Sorry, my fault, we wrong calculations. Okay, we will solve it ourselves, not on time. Okay, get it. My
Okay.
mistake, the calculations wrong.
Okay. 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 Okay.
Okay.
Okay. Thank God I actually stopped before solving it. I didn't realize sir also took from the same book. All right. Oh my God.
Is there any other question to be discussed?
Actually, we can solve another question. Mm, let's see whether I can bring it up. Just give me a few minutes, maybe 2 minutes or so. During that time, you can ask your question. Yeah.
Yeah, my question is pertaining to assignment 8. Uh,
Okay.
let me see. Question number 8, 19, not 19, 21.
Question number 21.
No, 22. Question number 22.
22. Okay.
You have given us the solution of that.
The propellant sliver mass in kgs. Is that your question?
Yeah, correct.
What was the problem with that?
I have another way of solving it, and I find though your technique is also correct.
Mm-hmm.
If you show us the propellant,
Mm-hmm.
you see, what you have done is in your solution, consider the whole cross-sectional area
Mm-hmm.
of the combustion chamber and subtracted from there the port area
Correct.
and the area of 4 rectangular parts. When the propellant starts burning, and it burns to the top, to the bottom, to the sides. So there are 4 rectangular parts. And then you have also subtracted the quadrants which are in the corners.
Okay.
That is your technique, which appears to be okay. The answer as per that is what is given here. I am using another technique.
Mm-hmm.
I'm not getting the same answer. It's just say geometrical calculations. Let's say if I extend the upper surface to the outside periphery, can you write on this with your pencil?
Sure.
Extend the upper surface of the port
Mm-hmm.
to the circumference.
1 second, let me give it a try. So we have.
Yeah, this is the port. The upper surface, if you dotted lines, you can extend it right up to the circle. The upper face of this, extend it to the,
Like this?
yeah, this way,
Okay.
both sides,
Mm-hmm.
and join those lines where it is meeting the circle, join together.
Okay.
Can join just not the upper part only,
Only upper part. Okay.
only upper part.
Like this?
This join together where they are meeting. Okay. So what you've done is there are such 4 rectangular parts that you have considered.
Hmm.
What I'm going to consider is, I know the length of the upper part is 0.5.
This one?
This also zero point 0.5.
Okay.
So I join these, where they are intersecting the circle, those points I join with the center of the circle,
Okay.
and make
Okay.
it a triangle. Ha. Now this triangle, you see where I'm joining is zero point 0.5. Again, the radius is also zero point 0.5. Radius of this
Hmm.
circle is also zero point 0.5.
Okay. This is also point 0.5.
The other side of the so it's an isosceles triangle.
Okay.
The vertex angle of this triangle is 60 degrees.
Okay.
Okay, so that is 1/6 of the whole circle.
Mm, yeah.
60 degrees, 1/6 of the 60 degrees.
Mm-hmm.
So the area of this quadrant
Mm-hmm.
from the center till the arc covering the whole thing
Mm-hmm.
is 1/6 of the cross-sectional area of the cylinder.
Oh,
Can we write that?
so could you repeat?
The area of this quadrant
Okay.
of the circle is 1/6 of the
Hmm.
area of the circle.
So you're telling this is times 6 is area of circle.
Correct.
Okay. Yeah.
So if I answer, okay, now I to find the sliver volume,
Mm-hmm.
of course the length you will multiply. I need to find out the area of the small strip at the top of the
Correct.
arch. So
Correct.
this area is equal to the area of the quadrant minus the area of the triangle.
Sorry to interrupt you, sir.
Uh,
Sir,
Yes.
I think the vertical length, I think it's not point 0.5, it's less than point 0.5.
No, not vertical. Vertical length I am not considering. The radius is zero point 0.5. So
Yeah.
that is the slant angle of the quadrant or the side arm. This is zero point 0.5. Is that right?
let's check 1 second. So
Yes.
total is 1. This is point 0.5.
And the
Uh,
radius will be zero point 0.5.
right. Right. Okay. Yeah. This will be radius will be point 0.5. True. So this will be point 0.5. This will be point 0.5. And since this is point 0.5, that will also be point 0.5. Okay. Correct.
So it's an isosceles triangle. The angle is 60 degrees. That means
Hmm.
the area of this quadrant is 1/6 of the area of the circle.
Area of the correct. Correct.
Okay, so the area of the sliver
Mm-hmm.
part is the area of the quadrant minus the area of the triangle.
Area of the quadrant. Ah,
Is
correct. So this part you are talking about.
yeah.
Okay.
This part is area of the quadrant minus the area of the triangle.
Correct.
So if this one part area, that is sliver part is over, multiply by 4 and multiply by the length, you get the volume.
Multiply by 6, right?
No, this area multiplied by 4 because there are 4 such pieces.
There are 6 such pieces, right? No?
4. Got on each side of the port.
Oh, okay. So you are talking about this thing. Okay. Okay.
Ha.
Okay. We have 4, right?
Yes. So
So
and
you are
multiply by
telling
this
this
you
should
get the
be
volume.
4 times
That area of the small
this part.
piece
Uh,
multiplied by the length. That is the volume.
hmm.
Multiplied by density, you get the mass, sliver mass.
Okay.
If I use this, is there anything wrong in this?
Uh, so one thing is, this is about sliver mass. What is this? What is it called? The sliver mass in kg.
I should get the same sliver volume as you have got. I'm not getting
Why
that.
have you considered this as a sliver?
This is the only sliver which is remaining. No, you have also done the same way. I mean, not same way, but you have also considered the same area contributing to saliva. Because when the burning phase has gone right up to the end, this is remaining to be burnt.
Mm, well, so this is like a final area you are talking.
Yeah.
So
This no, this I am only calculating at the sliver volume. Using this small strip, four such strips would be the sliver remaining after the most of the propellant has burned.
not necessarily. Why would that remain?
No, you see the burning surface area is receding normal to the initial burning surface.
Correct.
So when it reaches that point, the quadrant portions are burned fully.
Mm, so, but this is perpendicularly it goes, right? So everywhere
Yes.
it goes perpendicularly.
So perpendicularly, the quadrants are burned fully because it's going perpendicularly.
But diagonally also it's going, right? So
Yes.
probably I would expect finally it might remain something like this.
No, 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 no. The horizontal part will go horizontally only upwards. You
Mm,
can draw the instantaneous burning areas
huh.
from beginning till the end. You will find that the straight part, the edge, straight edge top, will remain straight only.
No, it can be turned. It can become like this.
Yes,
Why would
the
it remains?
curved path, the curvature will be only in the quadrant part. You know?
Correct.
Whereas the straight line path, if you vertically take up, it will remain straight only.
Correct.
So if it goes straight, it will leave the last bit, what you have hatched there in the quadrant,
Hmm.
that will be the sliver part remaining.
Sir, um, I think the diagram you considered, there is something. I think I think it's not correct because the angle, the way you considered, like you like extended the walls of the square till the circle, right?
Yes,
Hmm.
yes, yes.
So I think uh, I think it's not the approach. The the web thickness, uh, web thickness. I think we have to consider the web thickness here.
Correct, that is the web thickness. What is wrongly marked there, 0.5 on the side, that is the web thickness.
No, no. What I'm trying to say is that the uh, the sides won't extend till the circle. Like if we draw a point, if we draw a line from the corner of that square till the circle, like at a minimum distance.
Correct.
So, and if we draw a quarter circle there, so that length or that radius is less than the path you are extending it.
No, the quarter circle will remain the quarter circle. I am saying the horizontal part of the initial burning area will recede and will be maintained horizontally right up to the end. And the quadrant part will work radially outwards right up to the end of the cylinder surface. Am I wrong anywhere?
Mm,
I think the sliver burning is the burning when the what the photo.
No, what is marked on the screen here as a sliver, one part of the sliver, is that wrong or right? My conclusion, this is right. So there are four such pieces will, represent the sliver propellant.
right. So Give me a minute. I have to
Sir, the
understand something.
saliva burning starts after the area reaches the maximum.
Yeah,
Yeah.
after the rest of it burn, then only saliva burning starts. But our intention is not to burn the saliva. We want to find out how much is the saliva. We should know how the saliva is defined and whether what I'm saying here is the saliva part. Is this the saliva?
Mm, the sliver burning is systematic. One second. See, the balance of propellant left after the web burning is called the sliver burning.
Yes, yes. So
Okay.
the when you go, the horizontal part continues burning radially, vertically upwards,
Mm-hmm.
where it touches the corners, touch the cylindrical surface. Beyond that is the sliver, as we have shown here.
So okay, let's try to draw that also. So let's say if I do like this,
Yes.
this is the thing. As you said, maybe let's say we have this
Yeah.
square
This
here.
is
Okay.
yes.
Now you are telling this is going to be perpendicularly going up.
Going up right up to the point
Huh.
where it touches the circle.
Uh, that is true. But the sliver burning will start far, well before that.
Yeah. Like we just want to know how much is the sliver.
So the
That will
sliver,
start later on.
right? So when this is going to be after some instantaneous after some burning,
Yeah.
this is going to be
Yeah.
your surface,
Yes. 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 Yes.
right? This is just considering the
The,
straight surfaces,
yeah. Yeah.
right?
The state surfaces.
So now my question is, what happened to this?
Or you will be working there in a circular arc, joining these edges of red line that you've drawn. Yeah,
Exactly.
as a circular arc.
True.
So
Now,
that will form a quadrant of a circle,
right.
right up to the edge of the cylinder and end right up to the cylinder surface.
So now if I go through this, so then this part, the curved surface,
Yeah,
will reach this first
first, yes,
before this get reached there.
correct.
Before this part, this straight line reaches the this thing, the
Yes,
curved path will reach first.
yes, yes, yes.
So
That's my point.
once it reaches, you will have the sliver.
Oh, no, 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 hold on, hold on. Can you we go vertically, horizontal can be taken vertically up. This is not the sliver. Sliver is the last bit remaining.
Not really. So it's about once the web thickness is over, web burning is over, then whatever happens is sliver burning. So the web
Correct.
burning means everywhere it burns. So
Correct.
everywhere it goes out.
So we
So
need to calculate this radial distance,
hmm.
your web thickness, from the corner of the port till the surface. We need to calculate that, and that much distance, this will move up.
Okay, so one more question I have. What would be the web thickness for this?
That is the same as you have calculated. My web thickness is 0.1465. I calculated, rounded off to 0.15.
So my question is this
Web
web
thickness
thickness?
0.146, you can say.
0.146. So, but ideally, I guess this is
You
your
know,
web thickness.
in the solution also it is 0.15, rounded off to second decimal place. So it's the same. That is correct. So
It
if you move up both
okay.
corner radially outwards and the horizontal surface vertically upwards.
So, just give me a minute. Let
Ah,
me analyze this. So we have, let's say, I will draw this as a some coordinate system so that we can easily analyze. So in this is the initial empty. This is going to
yes,
be 0.25 and 0.25,
yes.
0.25 and 0.25. Now, um,
The radial would be 0.25 square plus
right.
0.25 square
So
root of that.
this will be the arc.
Yes,
Okay. So this is going to be 0.5.
Yes.
Now, now the question would be the web thickness should be this one,
Yes.
right? So how do we calculate that?
The radius, across the corners of the port will be 0.25 square plus 0.25 square.
So
Meaning, you take it
this
to
will be
the,
this one.
huh,
Uh,
the, the diagonal distance of the port.
so this part is going to be the diagonal.
Yes.
This is diagonal.
This is 0.25
Diagonal is
square, 0.25 square plus 0.25 square
okay.
root of that, and
Okay.
comes out to be 0.3535.
So web thickness, let's say delta is zero point 0.5 minus d,
Yes,
which is coming out to be
1465.
0.1465.
You can check that. I hope it's correct because that's what is the correct answer
Okay.
in the assignment.
Okay. Yeah, if it
So
is
the horizontal part will also move by the same amount.
the horizontal part, true, it will move by the same amount, but it doesn't have to reach the final, you know, the wall in order to
Correct.
take it as a sliver.
Correct, correct.
Before that, this will reach this part. This part will reach the this thing sooner. The reason is the reason is the distance the horizontal section has to travel is 0.25, but the distance this web thickness has to travel is only 0.146. So
Correct.
if the burning starts, it will be even. So this rounded edge will reach the sliver before the will reach the outer edge before the straight edge reaches there.
Let us see how much is the amount. The
Huh.
vertical distance you see is also zero point 0.5 in this diagram,
Mm-hmm.
coordinate XY.
Huh.
Vertical is a zero point 0.5.
True. True.
So the upper of the 0.5, 0.25 is the port. So remaining is 0.25.
Correct.
So that means that part is 0.25 minus
0.146.
0.1465.
Right.
That is the sliver part.
Uh, point two. Ha
0.25.
ha ha. Correct. 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 So it will be okay. Let me draw it in a separate graph also, so that
Now
it will
here
be
itself we can show
okay. Let's see.
the remaining part, and we can put the sliver here itself in this diagram.
Mm-hmm.
0.25 minus 0.1465.
So this part will reach here first, and there will be a straight line here, and there will be a
And
straight line here.
1035.
Right. So this will be some other length. Let's say we call it delta s, and here also you will get the same delta s.
Yes.
Okay. Now how much would that be? Um, it is going to be zero point 0.5. So delta s is going to be total is zero point 0.5
Sir,
minus 0.25. Yes, Pranav, go ahead.
sir, I think the the what I'm saying, the shape of the sliver remaining, it's not like a straight line.
Oh, yeah, yeah, yeah. That is
So
also
there's
there.
a curve
Yeah,
also.
yeah. It does curve.
The horizontal face of the port will horizontally travel, recede upwards. Okay, so there is a limit. That movement, the way it is recedes during the burning process, there is a limitation of over here point 0.5 is the total width. So this 0.25 will vertically go up as remain as 0.25.
Mm,
Yes, sir, I'm drawing the diagram. I showed in the camera.
yeah, sure.
Uh, it's pretty geometric
Mm-hmm.
actually. So wait just a minute. Let me pin myself.
Yes, we can see that.
Yeah, in this diagram, this part has a curvature. So when this part reaches here, this thing remaining is the sliver. So it will be an uneven one here. So if this is a curvature and this is a straight line, so this thing will recede inside, but this part we don't know the area of this part, right?
Correct.
So for calculating the sliver mass, you have to subtract this whole mass which has traveled.
No,
Hmm.
I'm not subtracting. I'm only saying the way I explained it. We need to find out the cross-sectional area of the sliver. First, we must uh, define what is sliver part. And then we find the area of the sliver. I have found it a different way instead of subtracting three areas from the total circular cross
Sir,
section.
sir, because it's not coming right because you're considering that it progresses
Hmm.
in in a manner of square shape,
True.
but it's not. It has a curvature there.
Curvature only in the corner.
Yeah,
And
in
it
the
will be
corner.
a circular quadrant, one fourth of the circle. That quadrant will be remaining as, that is not changing. And the horizontal will remain as horizontal. The quadrant will only keep on moving as the radius increases. The one fourth of the circumference of that quadrant, of the circle, will increase.
Uh, that will also have an effect in the interface motion, right? The surface motion.
So anyway, after they know whether what I am proposing is wrong or right.
So ideally, what we should do is we should calculate the sliver by subtracting it. So
Okay.
we cannot take it as a. Uh, so if we are doing that, um, yeah. So the reason is we don't know exactly how it regresses. So it is going to be perpendicular. So it cannot be straight lines. So as we drawn before, it cannot be like this. So it will not be like this green color, it cannot happen. So it has to happen like this.
Oh, this green line is not correctly plotted. It's not correctly drawn. It cannot happen like that.
Yeah, that cannot happen like that. Ideally what
These,
happens is it will be happening like this.
yes, 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 yes.
So
That's
what
what I'm
happened,
saying.
so what happened, this point has already reached, but ideally the edge is still curved,
Correct.
right? So which means I still have some web thickness, so I cannot call this as a sliver.
No, this not. The horizontal part of the port, you extend it to the top, it will continue going to the top. And when it touches the corner, touches the circle, that is the end of the main propellant. And then the after that, what is remaining is this sliver.
Okay, I understand. I think I understand what you're trying to say.
Uh,
So
if
this
you
is
draw
the
the here,
mm.
you
And
know,
then
and the port also you draw in the air, 0.25, 0.25.
mm, now
Okay, you draw the circle, quadrant of the circle starting from the corner and take this horizontal right up to the top.
okay, so you are telling I will follow this line, diagonal line, right?
Both you can draw,
I will follow this
correct,
diagonal line,
correct. Let the
and then
horizontal line be sent up.
mine will
Let's
go
not
from
like this. No, no, it's not correct. It's not correct.
okay.
Let the horizontal line recede and remain horizontal right up to the top.
Correct, but that will not tell us whether it has reached or not, right?
Oh, can you plot it at least?
Yeah.
Let this
So
blue line, horizontal blue line, go right up to the top,
correct.
where it
So
intersects the circle.
it cannot happen. That's what I'm trying to say.
No, and the join it with the vertical line from the corner. Both sides. Extend the from the corner of the port, horizontal and vertical lines.
So you are telling this should be my sliver, right?
What? No. This should be this sliver. That's what I'm saying.
You are telling this should be my
This
sliver,
should be this one. Yes.
but that will not happen. So sliver would have happened a little before, I guess. So
Well,
let's say,
the you see the web thickness is 0.1465. That is going right up to the surface. As it goes from the corner to the surface of the cylinder, it goes from the corner vertically up and horizontally also to the cylinder surface.
right, right, that is true, but mode has already changed.
No, the
So
vertical
I will,
surface.
let me prove you again. So let me prove
Okay.
you 1 second. So the sliver action will be starting once web burning is over.
Yes. Can
But
you draw the end of the web burning?
so when will the web burning will be over?
Can you draw this green line? Can you draw the web burning end?
Huh. So initially it will be like this, and it goes like this.
No, no, not like corner like this. The
Yeah,
circular arc.
yeah,
This
true,
has to
true.
be
Let's see.
where the arc starts. You can make it circular. It is not exactly circular. It should be the same circular shape as that of the red circle, that
it
cylinder.
it cannot be, right. It cannot be
By
the same circle.
I see the radius has to be maintained.
mm,
Circular arc means the radius has same. It's a circular arc.
so okay. Yeah, I think that is where the problem is. It will
Uh,
not be same.
Sir, in my video here, in my camera feed,
Mm-hmm.
here where the area it's not linear.
Hmm.
I'm just showing one fourth of that fiber.
Hmm.
So after it reaches the maximum surface area, so here it's not linear. There is an arc. There is some area here too,
Right.
right? So this is how the sliver look like, and the area of this part,
Hmm.
it cannot determine it directly from any formula. We can like subtract it from some another area.
Right, right, right. So actually, I think where the confusion is, so you consider the radius of this and that to be same. That is the main problem. So the radius of this curved edge of the propellant and the radius is not the same. So actually, radius is not.
No,
No, no, it
I'm
will
not
not.
talking about that.
Uh,
I'm saying from the corner of the port,
from
the
the
web thickness can be identified. From the corner of the port, how do you reach the edge of the cylinder to the cylinder surface? It goes radially outwards from the
correct.
corner of the port.
Right.
Don't start from the beginning of the center. Don't start from the center of the cylinder. Start from the corner of the port. Port means the empty space that you have where there's no propellant.
So from
So
here.
from corner to the cylinder, there is a radial progression.
Okay, so you are calculating from outside.
Like I will let me also
So okay.
let us see the
So
bicam.
based on this, my sliver mass would be something like this. It is certainly, I feel it should be higher than whatever you are telling.
I am also drawing the way I think. Okay, can you give me the sharing right map?
Sure, sure, sure.
Uh, that will be when I will do this. Uh, how do I let me see my videos?
Hello.
Okay, what I am showing here,
Hmm.
can you see?
I think you can share also if you have a.
No, no, I don't have
Okay,
this
okay,
copy.
okay, okay.
Is it visible?
Yeah, kind of, yeah.
Kind of.
Hmm.
So from the corner of the pore,
Hmm. Hmm, hmm.
there's circular arc. So the surface is receding and it actually is increasing. Every time the circular arc length is increasing right up to the cylinder. But the horizontal upper top will remain horizontal right up to the top of the cylinder. Both sides I have drawn. And now the top will reach at the same time the circular cylinder as the quadrant part.
Hmm. Uh, oh. Ha ha ha. So yeah, this cannot happen. This cannot happen. Okay,
This
let me
this
tell. Let me explain you. I understood. Okay. So actually, this will happen. Okay. So let. So okay. So let me draw the same thing you have drawn so that it will be.
okay. No, no, as we took a why are we doing this? Let's draw the port from first, and from the port we show how the propellant surface will recede, will progress, but how the burning will progress. Yeah,
Okay. So
yeah. Let us see how each surface will progress. No, not like this. The corner will go in a, yeah, in this fashion, a circular arc.
you are telling it will
It
be
will go,
something like this.
yes.
So
The
if you do that, if you
hmm.
do that,
And
the
maintain, let's have the draw the vertical lines of the horizontal and vertical surface also.
so
So the verticality of the surface, right surface, and the top surface that will be maintained.
I would say the sliver mass would be zero. If
No,
the radius becomes same as the outward
oh, no,
radius,
no, 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 no. This top surface of the port will remain horizontal, right up to the top. It's horizontal. So it touches the surface now. At some point, the remaining is this sliver. Anyway, what we need to do is draw in AutoCAD so that the area is automatically calculated.
mm, okay.
Anyway,
So okay, okay. I have another question. So you are telling that it will be straight, right?
yes, horizontals, no, no, not from here.
No, no,
The
no. I'm just
horizontal,
drawing something. One second.
correct.
Okay. So you are telling this part will remain same. After that, it will be a.
No, 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 I'm not saying so. I'm not saying so.
Hmm.
I'm saying the horizontal part of the port will burn, and the surface will remain horizontal as we go up, right up to the circle.
That will. Okay. You
Yes,
are
that's
telling
what I'm
this will remain.
saying. So on this vertical line, the left of it will remain horizontal only.
Mm,
Similarly, you can extend the horizontal line to the circle, horizontal line of the port to the circle, horizontal, this. So the quadrant will burn in a radial manner, the upper surface will burn, maintaining its horizontal surface as horizontal and vertical surface as vertical. That's what my point.
Mm,
Is that the correct
okay.
definition?
Okay, I understand the question now.
So others can also think of this. I think we'll close at this. Others can
Mm.
think of this and
Right.
peacefully.
Sir Ram, sir, I just
Anji.
think the area you are considering is the area when the flat faces
Yeah.
come in contact with this outer center.
Yes, yes. On top of that is a sliver. That's my definition of sliver.
Yeah, but I think I just reviewed the graph which the professor in the videos explained
Correct.
that the saliva mass is a mass when I think the area starts decreasing, like the
No, no.
surface
That
area.
will decrease only after that.
Yeah, it will decrease. So uh, when I think sir was saying that when that arc reaches the
Correct.
Weber radius, like
So
Weber
they
length.
will together reach this place. You see this, the web thickness in the radial side and the vertical side. They have to be same. So in the radial direction, it is reaching the cylinder surface. In the vertical direction, it is short of the surface. Only one corner is not touching.
Okay. So let's say, so this can happen. Okay, one second. Uh,
I think
so
we
let's
go
say.
back to professor's notes,
Mm-hmm.
and there he has explained web the sliver mass. He's defined it properly. So we can see that. Anyway, so the point I was making, I tried to calculate the sliver mass area. So that was coming different from what is there as a solution. So I want the clarification on that. We can leave it here, and maybe I will also think on that whether I am in the right line or is a mistake.
Sir, Ram sir, can you do some small calculation like the area you had you got, like the area of the cross section of the saliva mass you got,
Uh,
and the area you get when you follow their method, like the solution one
yes,
method.
there is a lot of difference.
I
My
think
mass of
yours,
saliva, you see, the area that I calculated is 0.0226, whereas in their case it is nearly double.
I think your area would be lesser than their area, right?
Correct, correct. So that's why I wanted to know why this.
Okay. So there is fundamentally few differences there.
Uh,
Um, the the okay, only if you want.
but I want to suggest, can we leave it at that? We let's say coolly think of it. Maybe there is a mistake from my side, there's a possibility. I will also coolly think of it and
No, no. I mean, uh, the argument you made is valid actually. So it is valid only when we have the curved edges and everything is regressing. Here we do not start with curved edges, we have pointed edges.
correct. The point X will develop into a circular surface.
Ah,
That's what Professor said. Okay, so we are considering from that point as a quadrant of a circle, the manner in which the surface will progress. The
so
corner.
that, yeah, that cannot progress it like this. It cannot progress like this.
No, it will progress in this manner like you have drawn here.
So
It is
okay,
correct. But
yeah,
my point is the horizontal part will remain horizontal, right up to the top. And when it touches the surface, that is the end of the, even the quadrant part also burning. They will burn together because the web thickness is same. In the horizontal part also, the web thickness by that time would have, got completed. The radial part would have touched the, it gone up to the surface.
So I am thinking this radius has to keep on increase. So this cannot remain like this.
Radius will keep on increasing. These
So why not?
one,
Why
the
not? It should not
circumference.
like. It should not happen like this. So why this and why it should not happen like this?
It will not happen like this because in the beginning it is a sharp corner. You have
I can.
drawn an arc right at the beginning. You have started on the wrong. It is not. It's not a rounded off corner.
Okay, so I
It
can
is a
even
sharp
start like
corner.
that, right?
You cannot start like that. It is a sharp corner. You see the diagram.
Mm-hmm.
It is a sharp corner. The port is not
Then
rounded off. If the port is rounded off, yes, you are right.
okay, okay. I I will think about it.
Ah,
I think something is missing here. That's
and there is a possibility. That's why the two approaches are not matching. There has to be some
exactly.
things.
But from web, okay, from the point of web thickness.
The web thickness remains same. You go radially is the same distance as you go vertically up.
Okay. So if we do the web thickness calculation, will we get the same thing?
Yes, 0.146 that you have written there, radially and vertically up, that would be same.
Okay. So
So when you go vertically up, by that amount, you would have touched, you would have gone right to the cylinder.
okay, let me just have a quick calculation. So
We'll
maybe
see.
web thickness is 0.146.
Uh,
D is 0.25.
Radial distance 0.147. By the time you reach from the corner, you reach the cylinder surface. So whether you go radially there, you go vertically there, or you go horizontally there, the bed thickness is same. After covering 0.146, you reach the end of the cylinder and the surface of the cylinder.
Okay, like this you are telling.
Yes.
And this is going to be okay. Let me draw
Mm,
0.396. This is at the end. 0.396, right?
Point, okay.
0.25 plus.
0.25 plus, yes, okay.
Okay. So now I have a pi by 4 into d square, which is 1 square, minus 0.396 into 0.396. Let's say,
No,
sorry, into 2.
okay,
Sorry, into 4.
into 4. Let's see what they do.
396 into 4. Pi divided by 4.
Acha, quadrant, you're considering, no, not 4, you're considering one-fourth of your circle.
So that's why I multiplied.
Pi d square by 4 is the total area. Okay, 4 into 0.3. This, that is my
So that
point.
area is coming out to be 158.
0.1465 and 0.25, 0.396. Right. Actually, 0.3965. There you go to 4 decimal place. Uh, so 4 into,
0.3664.
why are we saying 0.396 is the actually the is the distance, not the, no, you cannot write that as an area. This is not area. 0.396 is the gap
Distance.
distance.
But height also 0.396, right? So it's a
That
square.
is, no. That is not the area of the sliver.
Yeah, for order of magnitude analysis, I'm just trying to calculate. We know
Ah,
it's a circle, but I'm just
correct.
trying to understand.
Yeah, correct.
So this is going to be like a circle, but a little
Not here.
less, right?
Not here. The circle, by the time we touch, the circular arc will merge with the cylindrical arc. When it merges the cylindrical arc, the remaining part is the sliver. Oh, that is a 0.396 approximately. You're right.
That's what I'm telling.
Okay. So now 0.396 is the gap at the center. That is on the vertical ordinate here, on the vertical axis.
Mm,
That is the 0.396, that distance. 0.39, we have to calculate the area of this part.
mm.
Okay.
So that is what I did by subtracting it. How much is the area
Yes.
you are getting?
My point, my way of collecting, correct, calculating the area, I am getting area as 0.0226.
226 meter square. What is the correct area?
Uh, and then no, 0.0226, then I multiplied it with the, no,
4.
I have to find out here. Hold on, I just see that. So mass is this area, and the place. Now I calculated the volume as 0.9205. That's the volume. The area, so no, no, not this, not this. No.
Okay. Okay, anyway, I will think about it and I will come up with a better way of explaining it. Sure.
No, I found that your way is also right. I have done the calculations, it's talking about the same answer, but I
Mm.
want to know whether
Yeah,
this.
actually, it's a valid point. It's a valid point. When do we need to do like this? That is also a question, right? When should we do like this? When should we do the other way, right?
Uh,
That is also a question. It's a valid point. I will
the
come
next
up with a better
meeting,
explanation. Yeah, sure.
next meeting, I will also come up with proper pictures. Then I
Mm-hmm.
will make a diagram and I will share it here on the screen.
Sure. Okay. All right. Wonderful discussion. Any other problems with
You
any
wanted to
question?
discuss some questions. You said some other question you want to discuss.
I do not have the question.
Unless others have some question, I am
Huh.
okay.
Does anyone have any questions? Anyone have any other queries regarding the assignment problems?
So are we going to call it off?
Uh, Actually, let me take a picture of one of the question I have. Mm, okay, so I took this question from. I hope you guys can see it. Let me share it.
Sir, actually drew that a cross section of that of the sliver in a CAD program. Can I show it on this in a video?
Which program?
AutoCAD CAD program. It
Like,
actually geometrically plots everything.
okay, you did a CAD analysis,
Yeah.
something like that.
It just shapes and all. So
You should show that because you must have drawn the geometry using CAD, AutoCAD.
yeah, I'm using AutoCAD.
Let's have a look at the geometry.
Huh,
So,
you can share it. You can share it. I hope it's access is there for you.
uh, can I?
Maybe I will stop sharing.
She's sharing option there.
it is there.
You know, actually, I joined from my phone. Can I turn back camera on?
भैया स्विच ऑन कर लेना. मैं अभी ये वाला लाइट. हाँ हाँ. अरे भैया मैं फेस
Can you
वॉश
see
करने
this?
के लिए ना.
Oh,
मीडियम.
yes.
So here,
हाँ हाँ.
oh wait,
छोड़ दीजिए.
something happened.
आ,
So here there is a curvature. This point doesn't meet here on the circle.
ओके.
There is a small curvature here.
हम्म.
So and this is the sliver mass.
हम्म.
So and this point, this condition is what it's called. It has a maximum surface area of the burning right now. So
हम्म.
after this point, the sliver mass starts, right?
हम्म.
So it doesn't meet the circle here. This point, there's a tangent here. So this point doesn't meet on the circle. There's a small curvature. So we cannot calculate this small curvicular area. We can calculate this whole area and then we can
कैन
subtract it
सब्ट्रैक्ट इट. ओके.
like that.
या that is clear, but better explanation would be so. Yeah,
There is a point. There is a point in what he is saying. Yes, yes.
yeah, on that point.
I think Ryan should be seeing like the vertical or the flat surface goes ahead and the curvicular region vanishes.
Hmm. So it's
But
like a
that's
tangent to these two, right? Tangent to the circle and
yes, yes,
the straight line. That is how it
yes,
regresses. True.
yes. And when the saliva burning starts, that small curvicular region will start diminishing, but it won't diminish totally. So at the end, it won't be totally flat. So,
Okay.
Can you show that again? It's
Actually,
here. Here.
here, here is a curvature, and this is a straight line up till here.
and then you have a tangent.
So my point now is, in our calculations, we are considering that quadrant, the corner, is 1/4 of the circle.
Okay, wait. I'll do some. I'll tell you the angle of this thing. Wait. Ram sir, you considered 60 degrees, right?
No, yeah, I consider 60 degrees,
Yes,
yes.
60. So
Yes,
angle is
it's 60 degrees, yes.
Yeah, it is 60 degree.
the angle comes out to be 90.
No, you are not doing the proper touching.
Because sir, you considered a flat surface. So flat surface it touches those points to the circle. But here there is a small curvature at the ends, at the corners, and it's not flat.
Okay.
Yeah. So
So where it
actually,
is touching the surface, listen, Pranav, where
Yes.
is touching the surface, you join that line, make the triangle not from the radial distance, the point where it is touching the surface. You are making a triangle, where is, where is,
Yeah. Just wait a second. Here. So this is so this is the rectangular area, small rectangular area. Then there this radial thing starts.
okay.
So there is a small curvature here.
That would have got burnt.
Yeah, that burnt, but this condition has the maximum surface area, right? So considering this as a maximum surface area, this surface area should correspond to the saliva mass, right? That's why the area you calculated was less than this
Less
area.
than, yes, 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 yes. Yes. Okay, I'll also make the single down one and then see that. Yeah, you are fine.
True. That is great, Pranav. Yeah. True, true.
Actually, I'm totally gone by professor's explanation. So if you actually, I wanted to do that plotting. There's a good time, so I didn't venture on that. Uh, Clarify, it's okay.
Mm.
I will also attempt the same way and I'll have a justification of what he's saying.
Yeah, actually, I will come up with a better explanation how to do this in the
Okay.
next class.
Will be next time I will do, yes.
Yeah, yeah, sure. Okay. I think we are already 8:40. We won't be able to solve the other question.
Okay, then we
Maybe
can call it off.
we will call it off. If you have any questions, you can stay back and ask.
Yeah. Okay, thank you.
Sure. Thank you, sir. Thanks, Pranav. That was helpful.
Thank you, sir.
No problem. Um, Akhileshwar, do you have any questions you wanted to ask?
I think he's not there, so we can call
Okay.
him.
Yeah.
Okay, good night.
Uh, mm, the Millennium Academy. You said you have a doubt. Would you like to ask now?
Yeah, sorry, sir. Actually, I was busy in some work.
No problem. No
Okay,
problem.
okay, sir. Sir, actually, the inward and outward radial burning problem in assignment 8.
Mm-hmm.
Please explain, sir, how the burning starts. Either they simultaneously or how the initial area is calculated in the solution.
Okay, so since it's a inward and outward, both the areas are regressing together. Okay, so you have
Okay.
one area here. I'm sorry. So you have one here, and you have another here, right? So this is also a propellant, and outside is also a propellant. So you are
Sir, in the middle, this is propellant or the hollow part?
okay. It depends upon what is the color. So this yellow color is actually propellant,
Okay.
and it
Right.
radially inward and outward means it burns on the both sides. So probably you should calculate this surface area plus this surface area to be your initial surface area.
Right. Sir, actually, I was thinking that the central part is the hollow, so
Mm,
that's why I was
okay,
confusing about that.
okay. So you are considering this surface area and this surface area, the inner
Yes,
surface
sir.
area.
Yes,
Okay.
sir. Yeah, this set it as a inner surface area and the
Okay.
outer. Okay, sir. And one more question.
Mm-hmm.
1 minute, I will open the question.
Mm-hmm.
Sir, just 1 minute. Week 9. Yeah, sir. Uh, in question number 16, for this, the question number 16 is using the average burn rate of the propellant, the burning time in second for the outer grain. So, sir, in assignment, you take the length of the grain is 0.2, but here the given length of the grain is 1.8. So, The
Yeah,
propellant grain is 1.8.
correct. So,
So the 16 question, find the burning time for the outer grain. So you to in solution the burning the grain length is taken as zero point 0.2, which is the thickness of the outer grain, or
mm,
the, yeah.
okay, okay, okay. So actually, they are trying to. They are what are they asking? One second.
Yeah, so
Let me
question
let
number
me go back.
16.
One second. So let me see what are they asking. Using the average burn rate of the propellant, the burning time in seconds for outer grain, right? So
Yeah.
since the regression is going to happen like this, so regression is happening in this way, right? This is the way regression is happening, whose thickness is zero point 0.2 meters, and they are asking burning time. So you need to multiply RB times the thickness, right?
Sir,
Sorry,
here we take the length of the grain,
why we should take the length of the grain?
because the length the burn time.
So, okay, so I understand your problem. See, uh, the time for which burns is the length is going to regress together. Okay, so
Yeah.
if I draw this in this direction, this is going to be your the
Side view.
side view or the cross sectional view, and this is your central grain, right?
Yes, sir.
And the burning is happening in this direction. It is not happening in this direction. The burning is
Okay.
radially, right? This is radial direction. This is radial direction. This is axial direction. Burning is happening radially. So the time it takes to complete this section is going to be the time, is what they are asking, right?
Right, sir.
RB times the delta T, this thickness you should consider.
Okay, so for the end burning, we actually take the length.
For end burning, we should take the length because it is going to happen in this direction.
Right.
So by the way, what was this? RB is equal
Okay,
to.
sir. And in the second question, for the web thickness, in solution it was written as del max, but it is del minimum.
Which one?
The web thickness in the next question, the yes this.
Mm-hmm.
The web thickness in the solution it was written as del max, but it is the minimum thickness, so it should be written as del minimum.
I see. There's some problem with the question. Is
Yes.
solution, but the answer is
Yeah.
same, right?
Yeah, answer is same answer, no doubt, but the here you can see the del max is written. Yes, sir.
Del
Here.
max. Okay. Um, okay. Why did they say del max? Okay. There may be some convention they are following. Let me check the book they have done. Web thickness in the book. They have just used del. I think it's just a convention.
But sir, in the course lectures, professor said that
It's
it
a
is the
del.
minimum thickness, and the maximum thickness can be just from the top horizontal edge
Mm-hmm.
straight towards the circumference. This is the maximum. So, but the web thickness is the minimum.
Okay. Yeah. That is true.
And sir, yes, sir. Sir, it can be calculated as another way. We calculate the diagonal length,
Hmm.
and we know the radius.
Hmm.
Then the half length of the diagonal, radius minus half length of the diagonal will be the required web thickness.
Correct. Yeah. Radius minus half length of the diagonal. That is what they have also done, right?
Okay.
Radius is d by 2 minus half length of the diagonal is what they have done,
Yeah, right.
right? Right. Yeah,
Same
you're right.
like this.
You're right.
Okay. And okay, sir. Actually, I was absent from the start of the lecture. So, can you please just in a short time explain the silver mass, how it is calculated?
So the sliver mass is
Oh, sorry, sliver. Sorry.
okay. See that was the discussion we had. Um, See, sliver mass is simple. There is two kinds of burning modes. Okay, so one is web burning, another is sliver burning.
Okay.
Okay,
Yes, sir.
so
I have understand
mhm,
that the when the web burning is stopped, then sliver burning is started.
starts right exactly. So in web burning is when every surface is like all the surface is burning. uh, Sliver burning will be happening separately. Okay, so for example in the question given, uh, so it was like this, right? So is this the question you have? How do I calculate the sliver mass?
Yes, sir. The long formula which is given in the solution, how it is happened.
Okay, so let me look at the solutions once again. Minus plus b square plus 4bl. Okay, delta max l. So basically when the burning starts, okay, so this is going to regress like this, right? Now when you do that, here also this is going to regress like this. Okay, you just need to
Right.
find out when uh, the web burning ends. Okay, when could it possibly end? So you, so this is going to move something like this. Okay, let me draw one half of it. So this was the long discussion we already had anyway. So as this regresses, this is going to keep on going to go out like this, right?
Right.
So now the question is, so at some point, mm, so what happens is you will have this thing over here. Yeah, actually I'm totally confused about this.
Okay, sir. No worry. I will see the recording of it.
No,
It's
actually
not
there
an
was no
issue.
confusion. There was no conclusion there also. Uh, so I will look into this and I will come up with a easier explanation for you guys in the next class. Okay.
Okay,
So
sir.
probably it should be something like this, and this is the sliver you have to calculate. But the
Yes,
other
sir.
student here, they were telling that it should not be like this, it should be like this. They were calculating this small part, so they just extended it here. Okay. And then they were just
Okay.
calculating this small part. But what I am trying to explain is, I am trying to explain this small part will not be the sliver, this should be this part. But I don't have a valid
Right.
argument that what would be the proper curvature here. Okay. So
Okay.
yeah, so I have to work on that. Anyway, I will tell about this in the next class. Okay.
Right. Right, sir. Acknowledge.
Okay. Any other
Okay,
questions?
sir. No, sir.
All
Thank
right.
you so much, sir,
All right, no problem.
for. Thank you, sir. Sir, I am from Pakistan.
I see. May I know your name? Millennium Academy was your name?
Sir, Muhammad Ijlal Wasik. Muhammad Ijlal Wasik.
Okay, Mohammed Ijlal. Okay, nice.
Ijlal.
Okay, Ijlal. Is it?
Thank you, sir. Yes, sir. IJLAL.
Okay, okay. Nice meeting you, Ijlal.
Thank you, sir.
All right.
Nice meet to you. Okay, sir. Thank you.
All right.
Goodbye.